Welcome back, everyone. It's been quite a long break, and I'm finally resuming this course, so let's move on. We're gradually moving to more advanced topics, and one of them, which I believe requires some special attention, is the storage fundamentals topic. In this section, we'll be discussing some basic storage protocols, devices, technologies, virtual memory, and finally some storage virtualization. We'll first review some basic storage memory concepts that are mostly relevant to home users, and we'll then end up this presentation with enterprise storage fundamentals. That part would be a very good introduction to the way enterprises are managing their storage nowadays, and that part would be ideal for those of you who are interested in the data administration field. So let's move on. So we can start from first understanding some basic storage standards, protocols, and types of disks, and we can begin with the most common ones. So the first one is the ATA protocol or standard, which is a legacy standard for old hard drives. So ATA stands for Advanced Technology Attachment, and it serves as an interface that connects hard drives, CD-ROM drives, floppy drives, or any other storage devices. This standard has more than one implementation and has gone through different upgrades since the 90s. Then we have PATA or PATA, which stands for Parallel ATA. PATA is the result of a very long history of incremental technical development, which began with the original ATA interface. It is a parallel implementation of the ATA standard, which is also the original one. ATA and PATA are fairly the same, but the term ATA was retroactively renamed PATA only after the introduction of SATA, which we will discuss about later. PATA drives are also the ones we refer to as Integrated Drive Electronics or IDE and Enhanced Integrated Drive Electronics or EIDE drives. Now, in case you haven't heard about it before, we're going to talk about SATA as well. SATA is the most common storage standard nowadays. SATA stands for Serial ATA. SATA drives have replaced the PATA drives and use a different interface to connect to the device. However, the connection method is similar. SATA drives use a serial signaling technology which makes them way faster and much more reliable than PATA drives. SATA also consumes less power, has a lower cable length limit, and is nowadays the most common storage standard for HDDs and SSDs. SATA connects HBAs or host bus adapters to mass storage devices and operates in three different speeds. SATA 1 operates in 1.5 gigabit per second, which is equal to approximately 150 to 187 megabytes per second. SATA 2 operates in 3 gigabits per second, which is equal to 300 to 375 megabytes per second, and SATA 3 operates in 6 gigabit per second, which is equal to 600 to 750 megabytes per second. Now, some motherboards have ports called M.2 ports, which are used only for high-speed SSDs. M.2 replaces the mSATA standard, but can also run an SSD over SATA or PCIe. Next, we have the SCSI, also pronounced SCSI. SCSI stands for Small Computer System Interface. SCSI drives are quite similar to the old IDE and EIDE drives, but use a different interface to connect to the motherboard. The significant advantages of SCSI drives compared to PATA drives are their speed, their reliability, capacity, and their better fit for enterprise operations. Next, we have SAS drives, also pronounced SAS. SAS stands for Serially Attached SCSI and replaces the older parallel SCSI standard. While SAS refers to the interface type, it is typically used to describe a type of hard drive, usually 10K to 15K RPM. SAS drives provide a perfect balance between cost, capacity, and performance. They are much faster than SATA drives. They provide much more bandwidth, throughput, and reliability, and are mostly suitable for enterprise use and mission-critical applications. SAS operates in four different speeds: 3, 6, 12, and 22.5 gigabit per second. Next, we have the NVMe standard. NVMe stands for Non-Volatile Memory Express and is a relatively new high-performance protocol designed for accessing flash storage media in high speed and optimized for SSDs as a replacement for SATA and SAS drives, which were initially designed and optimized for HDDs. This type of storage directly connects to the CPU via fast PCIe interfaces and can operate almost twice as fast as SATA. NVMe often comes as NAND memory in physical form factors such as SSDs, PCIe expansion cards, M.2 cards, and much more. Now, to compare the significant performance differences between NVMe and SATA or SAS storage, SATA and SAS support one input-output queue at a time. SATA queues can contain up to 32 commands, while SAS queues can contain up to 256 commands. NVMe, on the other hand, can support up to 65,535 queues and up to 64,000 commands per queue. Many NVMe drives reach way over 500,000 IOPS, while SATA SSDs support only up to 120,000 IOPS. The following table is an example of how ONTAP, which is a storage management OS created by NetApp, reports disk types and how it labels them. So we can see that SAS disks are seen as performance disks and SSDs are seen as ultra performance. All the ATA and SATA standard is used for high capacity, and Fiber Channel or FCAL is labeled as performance as well. Next, we're going to talk about the differences between physical and virtual memory. This particular section is about RAM memory and not about storage, but you will see later on that following the same concepts, storage memory can be virtualized as well. So what is the physical memory? Well, the physical memory is pretty much every physical component that represents memory on the computer. For example, memory DIMM cards. On the other hand, virtual memory is the virtualization of RAM or random access memory by the operating system. So it's a memory management technique that provides an idealized abstraction of the secondary memory or the storage, which is available on a given machine, and creates the illusion of a larger quantity of primary memory or RAM. Virtual memory kicks in when the physical memory resources are running out. It is usually stored on the hard drives or the SSD and can be increased or decreased from within the operating system. Now, as it is stored on the hard drive, it is significantly slower than the RAM, hence it may decrease the performance of different applications and services. The area on the hard drive that stores the virtual memory data is called the page file. It holds pages of RAM, and the operating system moves data back and forth between the page file and the primary system memory. Another example of virtual memory usage is the hibernation mechanism, which exists on most laptops and desktop computer systems. Most users are not really aware of the actual difference between sleep mode and hibernation. While sleep mode turns off some visual features and power options, it is still running services and applications in the background, making it much more power consuming than a full shutdown or hibernation. The hibernation is a deeper sleep mode. It works by saving the content of the RAM to the disk and then shuts down the machine, so this mode uses no power at all. Once the operating system starts booting again, the RAM content will be reloaded from a hidden file which is stored on the system partition by default. However, it would take much longer to reload this system state from the storage to the RAM, as we have already learned that the secondary memory is significantly slower than the primary memory. Resuming the operating system from hibernation mode is significantly faster when done from an SSD. Both the virtualization of RAM and the hibernation mechanism depend on particular files that are stored as hidden system files on the active system partition, or the C drive by default. The first one is called pagefile.sys. This file stores the virtual memory data. When the RAM buffer goes full, Windows moves some of the data from the RAM back to the hard drive, placing it in the page file. The page file can be deleted in order to free some space on the hard drive, or alternatively, its size may as well be increased or decreased per the user's needs. However, although the operating system can function without it, deleting pagefile.sys is not recommended and may degrade the general system performance. The second file is called hyperfield.sys. This is a system file created by the system when your computer goes into hibernation mode. Hyperfield.sys saves the current state of your operating system before entering hibernation, so you can resume your work later on once you power on your PC. So on the right, you can see those two files in the root partition of your operating system, or the C drive. Now, be advised, you won't be able to see those files from your file explorer if you haven't enabled the display of hidden files on your system. So both hyperfield.sys and pagefile.sys are hidden system files, and therefore they are invisible to the user unless the operating system is manually configured to display them in the graphical user interface. This can be done in two ways. One way is opening a command line as an administrator and navigating to the Windows root directory by typing cd/ and then dir/a. This command will display those hidden system files and some of their attributes as shown in the command line screenshot. The second way to do it is from the Windows File Explorer. You find the folder option and click on the View tab. Under the Advanced Settings, check Show Hidden Files, Folders and Drives, and uncheck Hide Protected Operating System Files. Then navigate to the C drive and the two files will be visible. To customize the virtual memory and manage the location and size of pagefile.sys, follow the next steps. 1. Right-click on the Start menu and then select System. Then click on Advanced System Settings. Under the Performance section, click on Settings. Click on the Advanced tab and under the Virtual Memory section, click on Change. Uncheck Automatically Manage Paging File Size for all drives. Now you can delete, manage the size, or change the drive location for the system page file. As storage technologies keep evolving so fast and cloud computing is becoming more and more popular, storage virtualization is also becoming an essence. So we have already discussed primary memory virtualization, but now let's talk about the storage memory virtualization. So what is storage virtualization? Storage spaces, just like primary memory, can also be virtualized in a variety of ways. Storage virtualization can be briefly interpreted as the pooling of physical storage resources from multiple devices into what would be presented to the end user as a single virtual storage resource, or vice versa. A good example of storage virtualization is an enterprise storage controller managing multiple hard drives and virtualizing them to form a single unit. Although the terms we're about to discuss here are not a critical part of this module, nor of the entire hardware fundamentals course, they are of great importance in the world of storage and data centers, which is rapidly increasing its popularity. Whether you're working or aiming to work as a system or network administrator, a technical support specialist, a cloud architect, a database administrator, a virtualization expert, or any other IT-related area, you will, without any doubts, come across those terms, work with those technologies, or at least be required to familiarize yourself with their main principles. Let's discuss different methods used to virtualize physical storage resources. The first one is disk partitioning. This is probably the most primitive and basic type of storage virtualization, although it does not really fall under this category per se. Disk partitioning or slicing is the creation of one or more regions on a physical disk drive, so each one of them can be virtually and separately managed, whether for storing data, file backup, or even for installing an additional operating system. When exploring our file system using the Windows File Explorer, we would see by default only a single drive, the C drive, unless partitioning has been configured previously. Drive C is a specific partition which is allocated on the disk by default only for the installation and the deployment of the operating system. The rest of the space is considered what we called unallocated space. This space can be used to create new individual partitions depending on the amount of available space on the hard disk and how many partitions does the operating system support. Disk partitioning can be managed using the disk management utility in Windows or diskmgmt.msc. Now let's talk about volumes. Traditionally, most people tend to refer to partitions as volumes. However, in reality, volumes do serve a similar purpose but have different functionalities. A storage space that could be accessed using a single file system that the computer can recognize is referred to as a volume. A hard disk, a CD or DVD, or even a USB flash drive can all appear as volumes once detected by the operating system. You will notice that transferring a file between two partitions on the same physical disk will be way faster than transferring a file from the same disk to another volume. The reason behind this is that moving files within the same volume is typically done by just modifying the pointers on the file system, meaning without doing any physical alteration. However, when data is transferred between volumes, the actual data has to be physically migrated, which would be a more costly operation. Next, we have virtual disks. A virtual disk is a file that acts similar to a physical hard drive and simulate its storage capabilities, and from which it is even possible to boot an operating system as well. Hypervisors or virtual machine managers use those files to host their virtual machines and isolate them on their virtual physical layer. Virtual disks contain different file systems on which they can store different types of data or operating systems. The most common types of virtual disks are the VDI or virtual disk image, which is used by Oracle in VirtualBox by default. The VMDK or virtual machine disk is used by VMware workstations, VMware Player, and ESXi servers. The VHD or the virtual hard disk is used by Microsoft, Hyper-V, and Citrix XenServer. And lastly, the VHDX or virtual hard disk extended is used by Microsoft as well. Now let's try and understand the main differences between personal storage and the enterprise storage mechanism on private clouds. So what is enterprise storage? In enterprise environments, the storage is managed by very particular types of servers called storage controllers, which run a dedicated operating system for the purpose of managing and virtualizing the raw storage, serving specific business needs for their customers, or matching certain standards. Those systems would typically have their own network or be connected directly to the company's local area network to serve their data directly to the end users. Now, in those environments, disk partitioning, managed volumes, and virtual disks would always be in use for different purposes. So let's take a look at how raw storage is virtualized before it is presented to the end user. On the first layer, we have the physical storage devices, which is simply a collection of hard drives or SSDs installed on the same physical element. So we have a disk shelf or an array, which is a hardware element which contains a large number of disks and connects them to the server. Those physical drives will be virtualized by the server and combined to form a single storage entity from which only specific spaces will be allocated per client. So in the storage layer, we have disk arrays, disk shelves, and physical disks. On the second layer, we have the RAID algorithm, which serves as a data protection mechanism. So RAID stands for a redundant array of independent or inexpensive disks, and it is used as a method that combines a number of hard drives and set a data protection layer on top of them to make them even more redundant and fault tolerant. There are different types of RAID algorithms from 1 to 10 and DP and TEC depending on the manufacturer, which are used for data protection and performance improvements. So on the RAID layer is basically a performance and data protection mechanism that allows a group of disks to absorb one or more disk failures and to reconstruct the data from the parity drives. On the aggregate layer, we have a combination of either one or more RAID groups. So a RAID group is a set of disks that are configured to work under the same RAID algorithm. Aggregates are still considered as raw storage from a system perspective, and they can be expanded by adding more disks to an array, but they cannot be shrunk in safe and conventional ways. So aggregates are basically the aggregation of one or more RAID groups to form a single entity representing the physical raw storage. The next layer is the volume layer. So volumes, as described previously, serve the same purpose as a partition on a hard drive. However, in those cases, you can think about a volume as a partition within an aggregate. So think of an aggregate as a very, very large physical disk. And they can be used for the actual data storage and the file system. The file system itself will be created on the volume. So they're flexible and they can be modified, thin or thick provisioned for different purposes. They can be expanded or shrunk or even cloned or mirrored for backup. So on the volume layer, we have flexible partitions within the aggregate, which can be shrunk, expanded, and configured to serve all sorts of data. And finally, we have the LUN layer. So a LUN stands for logical unit number. Think of a LUN as a logical representation of the storage within a volume, but from the client's perspective. So once a connection from a client or an initiator to the storage system has been established, the client will be able to connect and read or write to the remote storage system as if it was a local hard drive. LANs are used only in SAN architectures in large enterprise environments. For small or medium enterprise environments, we usually see NAS architectures, which are more common, and storage would be accessed through a local file share. That's all for today. I really hope you enjoyed this session, and I will see you on my next video in which we will discuss the topic of read-only memory. Thank you very much.